Hello, in this video we present our work accepted by CVPR2023, Interactive Segmentation as Gaussian Process Classification. First, let's have a 1-minute overview of our work. In our paper, we provide a brand new perspective for interactive segmentation. For each image, we model the interactive segmentation as a Gaussian process classification task, with clicked or unclicked pixels as training or testing data. We then formulate the Gaussian process model and construct a corresponding framework which can guide information propagation and provide theoretical support for accurate predictions at clicked regions. Finally, we conduct experiments for model verification and demonstrate the superiority of our model. Let's introduce our work in detail. For the interactive segmentation task, a user iteratively gives positive or negative clicks on the image to refine the segmentation mask. Typically, the model takes the image, the clicks, and the previous mask as input to generate the output mask. Current deep learning-based interactive segmentation models generally perform pixel-wise classification without specific designs, and there is no explicit theoretical support that the clicked regions can be properly activated and correctly classified. To alleviate the above issues, we attempt to construct a Gaussian process-based framework for this task, because Gaussian process models can explicitly measure the relations between data points with a kernel function and can promote accurate predictions for training data and can be flexibly integrated with deep networks via deep kernel learning. Next, we present our methodology. Given the notations, we aim to obtain the posterior probability of labels at unclicked pixels. The right part of the integrand is the GP posterior. Once we get a sample from it, we can estimate the target probability with Monte Carlo method. So, how to efficiently sample from the GP posterior becomes the key step. The GP posterior can be written as such an integral. In the integrand, the first probability is Gaussian by definition, and the second probability can be further decomposed. For classification tasks, it is non-Gaussian, which makes the GP posterior intractable. Therefore, we propose to approximate the non-Gaussian part with a Gaussian probability Q, with its mean mc defined like this. We need to minimize their KL divergence, and we will add this term to the final loss. Now we can derive an approximated tractable GP posterior which is Gaussian. The standard approach to draw samples from it requires computing the Klasky decomposition of a star-by-star matrix with cubic complexity. This is unacceptable. To achieve efficient sampling, we adopt a decoupled sampling framework with linear complexity. Each sample is composed of a weight space prior term and a function space update term. Please refer to our paper for more details. Note that in the sampling framework, by replacing star with n, where n represents the clicks, we can derive that the predicted classification scores have the same size with their labels. This provides theoretical support for accurate predictions at clicked regions. Based on the efficient sampling framework, we can easily construct the entire network with clear working mechanism, where the deep kernel learning technique is adopted in both weight space and function space for better flexibility. Next, we present our experimental results. We visualize the decoupled GP posterior, showing the rows of the prior term and the update term. We further validate the theoretical support for accurate predictions at clicked pixels. The epsilon here is a small number to avoid singularity of the kernel matrix. We can see that with epsilon getting smaller, the number of incorrectly classified clicks over the database dataset becomes smaller. In the figure below, the baseline method RITM repetitively clicks on the same position because it cannot have accurate prediction in that region. In contrast, our proposed method can finally alleviate this issue. We adopt segformer, HRNet, and ResNet as the backbone segmenters. In this table, the experimental results over 4 widely used evaluation datasets clearly show the superiority of our proposed method. We further evaluate on more metrics to demonstrate our superiority. Note that our method has negligible increases on number of parameters and inference time. We also provide more visual comparisons with the competing methods. Thank you. Feel free to leave a message if you have any question.